Hello everyone. Thank you for watching my presentation video of the short paper Crowdsourcing Detection of Sampling Biases in Image Datasets. I am the first author, Xiao Hu. The work was conducted along with other students and professors from Purdue University and Loyola University. Nowadays, computer vision has been applied to various domains, but researchers have found that there exist a number of risks in the current computer vision systems, suggesting that the results of these computer vision algorithms can be unfair or untrustworthy. For example, a trained image classifier would classify the left bride photograph as bride, dress, women, or wedding, while classify the bride photograph on the right as performance art or costume. Also, researchers have discovered that modern commercial face detection softwares generally have better performance on images of lighter skinned males compared to darker skinned females. After looking inside the training process of the computer vision algorithms, researchers realized that one possible reason for the trained models to be biased could actually come from a biased training dataset. For this bride classifier, training data comes from the widely used ImageNet, where it contains 45% images from US, but only 3% images from India and China. Such lack of geodiversity partly explains why computer vision algorithms tend to assume that a bride image should always come with a white dress. Similar story happens for the face detection softwares. The percentage of photographs of white males in the training data is much larger than the darker skinned females, which led to higher facial recognition accuracy to a certain groups of faces. On the other hand, humans have innate capabilities to understand images and identify patterns in images. This led us to the question that can the crowds help detect the sampling biases in the training image dataset? If yes, how should we present the images to collect meaningful inputs from the crowds and therefore analyze the input image datasets? In this paper, we present a three-step crowdsourcing workflow that successfully combines the intelligence of individuals and converts them into statements describing biases of the input image dataset. In step 1, we ask crowds to describe the similarities they found among three images shown on the page and then narrate them in the form of a question and an answer. In step 2, we collect the answers of the questions generated from the previous step with more images. And in step 3, we rephrase the questions and answers from the previous steps into a statement and ask crowds to judge the statement's accuracy based on their understanding of the targeting object in the real world. Each step was completed by different groups of crowds, so we can avoid potential biases brought by the same people as much as possible. And next, I will give more details of each step in our workflow. In step 1 question generation, we randomly sampled three images and showed them to the workers on the left side of the screen. Workers are expected to find the common features among these three images and then narrate each one of the features into one question and an answer on the right side of the screen. We ask crowd workers to start their questions with what, where, when, and how to improve the quality of the inputs. For example, for these three images of airplanes, a possible question from the workers could be, what is the direction are these airplanes facing, with the answer right. Eventually, the output of step 1 would be a set of questions where each of the questions can represent one bias of the images. However, crowd's inputs are noisy. Same features can be interpreted by different words, although they actually mean the same thing. To maintain the diversity of our inputs, we use a natural language processing tool to merge the similar questions together by checking the similarity of their phrases. For example, as shown in this slide, question what is the direction this airplane is facing and the question how are these airplanes facing will be merged into one question. After filtering, each question from step 1 would represent a unique bias in the images. With the step 1 outputs, you may think, why not just stop there with the questions describing biases? The reason why we still need the next step is because that some similarities may apply to certain images, but not all. For example, if the common feature among these three airplane images was they all belong to United Airlines, it may not be true for all the other airplane images. Therefore, we want to find the distribution of the answers regarding the questions on the most images. And in this way, we can understand the distribution of a similarity within the entire dataset to gauge how likely it is a real bias. In step 2, answer collection, we collect answers for each question and estimate its answer distribution. Workers are expected to answer all questions from step 1 based on different samples of images showing on the left side of the screen. We provide a skip feature allowing workers to skip a question if they find it does not apply to the majority of these 4 images. If one question is skipped by a lot of people, that question is probably not representing a majority shared similarity and therefore will be discarded. Eventually, we have a list of questions where each question has several answers attached. After step 2 answer collection, we apply the same merging mechanism to each question's answers and find the answer that is weighted the highest. Eventually, we merge each question answer pair into a statement as the input to step 3. For example, the question, what is the direction these airplanes are facing, with the answer right, will be merged into a statement saying, with most airplanes, the direction they're facing is right. In the last step, bias judgment, we show the statements to another group of workers and ask them to judge whether statements of the dataset reflect the real visual world. For example, the statement, with most airplanes the direction they're facing is right, could have majority vote on no, indicating this statement is not true in real world. Finally, we sort the bias statement list from the most voted to the least voted as the final output of our workflow. Then we conducted 2 evaluation studies. In the first study, we wanted to examine whether the crowds can detect the sampling biases that we intentionally injected to the datasets. The 120 input images were selected from airplane class from Caltech 101 image dataset. Within these 120 images, we intentionally designed the proportion of features to be 100% images with the airplanes facing right, 80% images with airplanes on the ground, 80% images of large commercial airplanes, and 70% images of white airplanes. These biases are considered as our ground truth for this set of experiments for the crowdsourcing results. After that, we released the tasks for each step on Amazon Mechanical Turk crowdsourcing platform and collected inputs from crowds until each image or question is reviewed by at least one worker. The results of Study 1 shows that the crowds generated 32 bias statements in total, and not only 4 injected biases were detected, crowds also found some additional biases in the images, such that the weather in most images is sunny and the photos are taken during the daytime. In order to have a better understanding of the results, we classify the 32 bias statements identified by the crowd into 4 categories. Both known biases and the additional biases are considered as correct biases detected by the crowds. As you can see, both the bias category percentage and the top 10 bias statements proves that our workflow actually can provide reliable information of the image dataset biases. Finally, to see whether the ranking produced in Step 3 provides reliable information on how likely each statement reflects actual sampling biases of the dataset, we compute the precision and recall for all 32 biases. The area under the precision recall curve is 0.893, suggesting that Step 3 ranks correct bias statements higher on the output list. In summary, our evaluation in Study 1 suggests that with respect to the artificially created small image dataset of airplanes, our workflow can effectively guide the crowd to discover the biases of the dataset. To see how well our workflow works on real-world image dataset, we randomly sampled 600 images from the car class of ImageNet. The ground truth of the experiment was 21 biases detected by 6 experts jointly. These experts are researchers have at least 2-year experience in computer vision related research. Then, same as study 1, we released the tasks on Amazon Mechanical Turk for each step with the different groups of crowds. The results of study 2 showed that 15 out of 21 experts detected biases were also detected by the crowds through our workflow. Same as study 1, crowds also found 7 new biases that were not detected by the experts. We conducted the same annotation for all bias statements generated for study 2, and here is the annotation result for the top 10 statements. Again, most of them represent the correct biases. Based on the bias statements generated by both the experts and the crowd, the precision score of the crowd is lower, but the recall score is much higher than the experts. This result tells us that it is reasonable to use crowds to participate in our workflow to have a more complete understanding of the biases in the image datasets. In summary, it is possible to leverage the wisdom of crowds to detect sampling biases in image datasets. Through 2 sets of evaluation studies, we found that the crowd can effectively discover a more complete set of biases in real-world datasets using our workflow. The plan for our following development includes 2 parts. First, we will explore methodologies to help us summarize the dataset with representative samples to improve the efficiency of workflow. After that, we will analyze sampling biases of more widely used image datasets to provide more understanding of image dataset biases for the computer vision community. If you're interested or have any questions about this research project, feel free to ask any questions now or email me at hu440@purdue.edu. Thank you very much.